それでは、時間になりましたので、これよりセッションを開始したいと思います。ジェイミー・トンプソンさんによるスカラ3ビデオ時間を最適化です。どうぞ。
Hello. Yeah, so my name's Jamie, and thank you for inviting me to Scala Matsuri. It's my first time in Japan. I'm enjoying it so far, really great. So I'm going to talk to you today about build tools and the Scala compiler, and basically the work I've been doing to make it a bit faster for some projects out there. So the first thing I'll introduce, if you're not so aware, is just kind of a little bit under the hood. What is a Scala build? How does it work? Then the next thing is I will review the past work I've done over this year from 2023 to 2024. The work I've done to basically improve some performance of building Scala code. And then I will also review a bit about what could come in the future, some work that we started. So a bit about me, I work for the Scala Center, which is basically this nonprofit organization, which you could say is a sandwich between the research that happens at the University EPFL in Switzerland, which is where Scala originally came from. And then we're also in between the industry. All these companies use Scala, and we also collaborate with and try and promote the Scala open source ecosystem. Some things that we've worked on. Oh, by the way, there's my colleagues in the picture. We've worked on Metals, which is the IDE for Scala. Scala.js, we do all the maintenance for that. Scala Dex is this website where you can go there and find all the Scala libraries that you can use. SCSD, online playground for Scala. And we're currently working on porting SBT to Scala 3, and that will be SBT 2. And we've also done a lot of work recently on the Scala debug adapter, which hopefully will be sort of a platform for having a good debugger with expression evaluation and a stack trace that is actually showing the real Scala signatures. But yeah, we're still currently looking for more corporate partners to help us do more work, because currently we only have 3 engineers. And if you'd like us to continue doing really cool projects, then please consider sponsoring us. You could talk to me later. I have a this orange t-shirt. Okay, so what is the Scala build? Basically, I'm going to be talking about a bit about performance. So just bear in mind that any sort of hyper optimization could be misled. So don't focus too much on optimizing, but we'll talk about this. So what is the build tool? Ignore Scala CLI in the middle. It's not a build tool. That's what they say. But yeah, all these sort of things you could consider basically operating on the same architecture. So we have like SBT, Mill, Maven, Gradle, Bloop, and Scala CLI. They all use the same architecture. What is this architecture? There's basically 3 layers at different 3 layers, and each layer has a different level of abstraction. So at the outer layer, we have basically the build tool, which basically models the idea of a project and what is a project, and sort of the details of publishing projects to Maven Central or packaging them or something like that. Then you go one step layer down, which is at the individual project layer. At the individual project level, how do we build a specific project? And in the Scala stack, we have this tool called Zinc, which is an incremental compiler. And that basically means that when you edit a file, it should be fast to recompile because you only compile the changes. And then at the very lowest level, we have the Scala compiler itself, which all these tools wrap and build on top of. So going back to that top layer, which is in this case SBT, you can imagine that, yeah, we have a project with 3 subprojects, common, and then client and server, where they both depend on that common. And you're going to supply some high-level information, such as the name of a module, which library dependencies it depends on, the sources that it has to compile, and the outputs of this. Like maybe some source generators as well. So if you have a protobuf generator to run. Then going down, looking inside, then yeah, we actually have the operations that the build tool does. So for example, if this common depends on OSLib, then you're going to say, SBT, please go and fetch this library off of the internet somewhere, which is going to be probably Maven Central. And it's going to do generation of sources from protobuf. And then basically it has to schedule the building of these projects so that common goes first, and then you have these other ones. So let's say you have basically a graph, a more complicated project. It could look like this. And then basically the graph of dependencies makes a directed acyclic graph. So common at the top, then these ones, and basically they're color coded because they can be done in parallel. So let's imagine you have a timeline where you're building each project. We can have common first, and then as soon as common is done, we can schedule all these 3 to happen immediately because they only depend on common. And then next we see the client only depends on API. So as soon as API is done, then we can schedule client. But server has to come in a separate group because it depends on all 3 of these red ones. But let's look at a specific chain. So common, then API, then client. What is really going on here? So common, we know that its inputs were the files in the common directory, and it's going to output this common jar. And jar is like a zip folder. It basically packages all the class files and tasty files, all the artifacts that are necessary for someone to use that module, whether it is locally on the machine or uploaded to Maven somewhere. Everything that's needed is inside this jar. Then we see that API, in its inputs, it requires that common jar. And yeah, its sources are also in API, and it produces API. And then client needs both the API jar and the common jar and produces its own client jar. So yeah, if we want to look at a specific project, let's go in deeper by looking at the next level down, which is Zinc. So Zinc is basically an incremental compiler, and what that does is it adds a little bit of abstraction over the top of the Scala C compiler, which is lower down, but it's more specific than the build tool layer. So some things that it does abstractly is that it can virtualize where files come from, whether they come from a build cache, which could be on the internet somewhere, or if they come from your disk. And it also maintains the Scala compiler in memory so that the Java virtual machine can JIT optimize it to make it faster. And it also is able to track changes in source files over time. And yeah, the purpose is to only compile what is necessary to build code that was changed. And it also supports cancellation. So what is basically this incremental compilation algorithm that Zinc does? Let's say you have never built the project before. You have all these source files. So the first time you're going to say compile, then basically it will compile all these files. Then let's say you make an edit to file A, then basically Zinc can detect that only A changed on the file system, so it's going to compile that. Then when it did the first compilation, it basically tracked how each file depends on each other. So it knows that when you compiled A, that actually D and F, they actually depended on some sort of definition that changed in A. So then they will be scheduled to compile. And then once we've compiled those, let's say, for example, then nothing else needs to be recompiled. And hopefully the goal of this is that this is faster than compiling every single file. I talked about this in much more detail in my Scala Days Seattle talk from 2023, which you can see on YouTube. But yeah, now let's go down to this more lower level, which is the Scala compiler itself. So this is what it does. It gets those very low level inputs, such as specific source files, specific jar files. And for example, you have an external class path option, which supplies, for example, the Scala 3 library. And then it sends all those files through a pipeline that transforms them over time to produce several outputs. So the API jar that I showed earlier, and then you have class files and tasty files. And class files are the artifacts that actually run code on the Java virtual machine. And tasty is this format that stores the signatures of your code such that when you download a library from the internet, then you can read the definitions that are inside that library and know how to interact with them. So if we do a little X-ray onto the compiler, on the compiler pipeline, it's made out of these little modules called phases. And each phase is basically responsible for doing a small transformation, a very specific transformation on every single source file. So the very first one, for example, is the parser phase. And that is what basically reads all the text source files on the file system and then transforms them into the compiler's own internal representation of code, which is called an abstract syntax tree. And basically check that the syntax follows the correct rules. Then the next phase is going to be the typer phase, and typer basically traverses those abstract syntax trees and checks that they're correctly formed, such that, for example, the type checking is correct, that you didn't make any spelling mistakes, these sort of context-sensitive rules that must be checked. Then you go through some other phases, such as the dependencies phase, which is part of the incremental compilation algorithm. So it checks in each file, it says, which are the symbols that I used from some other file. Then we have this pickler phase, which is very important because this reads the syntax trees and then produces this format called tasty, which I just explained earlier. And this is where it's produced, and it's quite early in the compilation pipeline, which is important for this optimization later called pipelining, which I'm going to introduce. And then after that, we have the API phase, which is again used for the incremental compilation algorithm, basically to track changes in signatures so that we know that, if you change a method's return type, then we know that everything that calls that method needs to be recompiled. So we track that signature here. And then you would go through several other phases where we basically take your code and make it simpler and simpler and simpler until we reach the back end, which is where we produce those class files, which are necessary to run the code later. So if I have a little tip for you, if you want to improve the performance of your build, is basically if you use smaller files, then this means that when Zinc does the tracking of dependencies, then you have a more fine-grained graph, which means that, maybe only less code needs to be compiled at a time, rather than, one line change in a 10,000 file would be super slow if you had to recompile that. So use small files. And another tip for better performance with Zinc is basically if you have one giant project with hundreds of thousands of files, that's quite extreme. Maybe 500 files is more reasonable. If you can, try splitting that into smaller modules, say like 20 files per module, if possible. The reason I say that is because, like I showed earlier, we can schedule things in parallel, which definitely improves the performance of your build, because by default, the compiler is single-threaded. But conversely, don't make your projects too small, because this can lead to many things such as thread starvation or a lot of duplicated work. So there's a balance there. So now I want to talk about some of the work that I've done over the past year. So this includes pipelined builds, and let's look forward to the future. Yeah, so one of the things that sort of landed in Scala 3.4 is better support for the remote caching feature in SBT. So this was supported in Scala 2.13 as well for quite a while. But yeah, so now we better support this idea of remote caching, which relies on this virtual file system that Zinc has. So yeah, there's been a lot of talks recently at Scala, for example, about remote caching. That basically means you can, if your team has the resources, you can basically build your project, upload it to the cloud, and then some members in your team, they can basically just change the file and then it downloads what was already compiled. So you don't have to build the whole project again. And yeah, there's this blog post where someone mentions how they were using it. So it's a good thing. You should try it out. Yeah, next, this is a feature I implemented. Basically, progress tracking is this thing where basically we could say, how far am I through the compilation? So in this little GIF, we could say like, this is from Lichess, and I'm saying, oh, we are 90% way through, 75% way through. Previously, before Scala 3.4, this was always frozen at 0%. So it's basically a nice little enhancement. Yeah, you might be wondering like, why do we have a progress bar? Aren't they all sort of fake to basically just convince the user that you're doing something? But this isn't fake, and this is how it works. So basically, we can say, imagine that the total amount of work is basically the product of the number of files and the number of phases. That's the total amount of work to do. And then your current progress is like, how many files have you compiled? How many phases have you gone through? And then in the current phase, how many did you see in the current phase? And then the progress is just divide the current by the total. And we keep updating this progress every single file in every single phase. So let's say you had 4 files. Yeah, then basically at the end of the parser, you have 3%, end of type is 6%, and so on. And then at the end, you get 100. Hooray. But this feature also introduces better support for cancellation. So this giant button is like the cancel button in Visual Studio Code. So you can cancel compilation, and basically after the end of each file in each phase, we do a check to say where we canceled, and then we actually stop the compilation. Before, you had to wait until you got to the very end before you'd even bother trying to cancel. So it didn't cancel at all, basically. So this is better. Next thing, I'm happy to say that finally we have in Scala 3.5, we're going to have pipelined build support. It's also available in Scala 2.13, but now it's for the first time in Scala 3. And what is a pipelined build? So going back to that example where you have perhaps 3 projects, 3 sub-projects in a build, and well, I don't know why this says project D, it could be project C, but let's say D depends on B and B depends on A. So this is the best way we could schedule it, even in a multi-threaded environment. What pipelining allows you to do, and this is how you turn it on with this build use pipelining. Yeah, it basically allows you to schedule project B to begin even earlier, even though it depends on project A. One thing to note is that this only works if the project doesn't define any macros. So yeah, if you don't have any macros, then this is a good idea to try and turn on. And how does this work? So going back to the compilation pipeline, typically what happened in the past is that these tasty files, which are the thing that's necessary for a downstream compilation to begin, were produced at the very end in this bytecode generation phase. But when we turn on pipelining, now we're allowed to produce these tasty files at the pickler phase instead. And this is something that's about 30% through the compilation. So what this means is that when we reach pickler phase, then we're going to produce a jar file that contains only tasty files. And as soon as we have that jar file, then that's what's necessary to start a downstream compilation. So your mileage may vary in how much it improves the speed of your build. But for example, a good project that actually does benefit quite a lot is the Scala Dex project. And this is what it looks like. So it has at least 4 levels of dependencies. So that means that the compression of starting something before the project to buzz is finished is that basically is maximized. So you get a lot of speed up there. And this is a project I did for myself. This is my own project. So I can show you at the end how fast it speeds it up if we have time. But yeah, this is basically real profiling data that I recorded. So it has 4 projects and it basically takes 4 seconds to compile. And then when I turn the pipelining on, then it takes about 2.5 seconds. So this is like more than 1/3 faster, more than 33% faster. So it's a very significant speed up if your project is, if your project layout is in a specific way. Yeah, and yeah, basically each of these things is a rainbow because like each of these bands is one of these phases. So this green one, which takes a very long time, this is the inlining phase, and inlining happens after the pickling phase, which is here. And so basically once we reach the pickling phase here, then we can immediately start the downstream project, and then we don't have to wait for all this stuff. So, depending on how your project looks, it can really give you a big speed up. Yeah, so if you do have macros defined in your project, and a macro is not the same thing as an inline method, is specifically a macro method, then you should turn off pipelining because basically it's not it can lead to errors, and this is one of the errors that you'll see. Basically, you try to call this macro here, and it's going to say like, oh, I couldn't find this object that was necessary to run the macro. And the reason is because pipelining doesn't include class files in its output, but class files are necessary to run a macro. Yeah, so again, I gave a longer talk about this at Scala Days 2023. And yeah, that was June, literally like exactly 1 year ago. So this is when I first talked about this at Scala Days. Then in July 2023, we then added the ability to support these tasty only class paths in Scala 3.4. What that means is that before, when we read a library from Maven, we had to look for a class file first. And then when we knew we had a class file, then we looked for a tasty file. Now we can just look straight for tasty files only, which is a necessary step for this project. Next thing, at the end of July, we finally supported the Zinc 1.4 and above, which allowed us to do that build caching feature. Then by October, I'd finished the compile progress tracking. And then by November, basically I got to this point where one of the features that's really important for pipelining is that controversially, we have to compile Java source files to Tasty. And the reason we do that is because we don't want to wait for the Java compiler to finish. So the Scala compiler already reads Java files, if you didn't know that. That's how you are able to read a Java definition, because it actually type checks the Java file for you. So this is kind of what it looks like if you print Tasty in a human readable way. We have an entry that describes the trees in the file. So let's say you had this Java file, just a class A with a method foo, and we have printing out hello here. So the class A gets represented as this type definition with A, and then we have inside here a method definition for foo. And then one of the new features in this Tasty is that we actually avoid serializing the bodies of methods, which is a performance improvement, because with the pipelining, we only care about the signatures. So we only care that it returns void and it has no arguments. So empty clause means no arguments, and this is a reference to void, which is unit in Scala. And then we had to add this attributes section to say, oh, this is a Java file. And this outline attribute means that we're skipping the method bodies. So this was a new feature we added in November. And then by February this year, I added the support for pipelining into Scala 2.13 that to read things compiled by Scala 3. So this is a feature that's been around for a while with this wide tasty reader flag. And that basically allows you to read Scala 3 libraries from Scala 2. And this is a great help for migrating projects, because if you have 5 modules that all depend on each other in a build, then it's quite hard to change the Scala version. So if you add this tasty reader flag, then you can change one of the modules to Scala 3, and they should be able to just exist with each other. But in order to turn on pipelining, you need to be able to read pipelining code from Scala 2.13. So I added that feature before this year, which also means having to read this Java tasty from Scala 2. Then by the end of February, yeah, we completed the Java tasty. So basically there was some bugs in the type checking. So that was needed to be fixed so that we were equivalent to the class file format. And then finally, by April, we finished the pipelining, and that is scheduled to be released properly with 3.5.0, but there's already the RC1, and RC1, you can try this today with pipelining. Yeah, and then a small enhancement is that now we write this tasty in parallel, so we don't block the thread while we're writing the tasty. So yeah, I think I don't have time for that. So let's talk about the future. One of the things that we want to do is basically shift more things to background threads. So currently, before I showed that we have, for example, this API phase and this dependencies phase in the main thread. but we would like to be able to do them basically after we produce the tasty. So we run the pickler phase, and then in a thread, we're writing this tasty. And then the idea is that semantic DP generation, dependencies tracking, and API extraction can all be done from tasty. So the idea would be to shift all this to a separate thread, and perhaps we'll save some time. And then another feature I wanted to work on, but I haven't had much time to do it, is this multi-pass compilation. So again, this is what a compilation looks like for the Scala 3 compiler, for example. And that's a visualization of all the phases. And if we turn on this thing, which basically, you see, it's a lot shorter. So we managed to cut these phases up to the yellow line by a huge amount, and including this type checking phase, which goes very, very short. And what that is we're using this outline type checking mode, which skips all the bodies of definitions. So that's why it can be a lot shorter. And that the benefit of this is that this yellow line is where we can start the pipelining from. And so that means downstream projects can begin a lot earlier, which improves throughput. And what we can do next is basically run the compiler again to produce the class files. So this front part only goes up to the pickler phase. And then this bit again also starts parsing, type checking, etc. But we can basically split the work into batch jobs that happen in parallel. And this leads to actually, 1/3 of saved time if you use 3 worker threads. And yeah, what's the concept that's going on here is like we have the same source files, but we split them into batches. So then this one does like 1/3 of the files, this one does another third of the files, and this one does the final third of the files. And they see the definitions from each other's files by using the tasty that was produced at the pipelining. Another mode we're also thinking of doing is perhaps this batch compilation, which is an alternative to that outline type checking. And this is where instead of having 2 passes, you have 1 pass, but you do it in batches. And so you would say batch A, you're going to compile fully A and B, but then you'd only outline compile these 2. And then batch B is the opposite. You're going to fully compile D and E, but outline compile A and B. And then perhaps, I haven't tested this yet, perhaps it could save some time. But, there's a lot of duplicated work because instead of compiling 4 files, you're now compiling 8 files, but only sort of duplicating some of this work here. So it's worth checking out. Anyway, so here's some benchmarks that I recorded like June last year. So this is quite old at this point. So the compiler might have got slower or faster since then. I don't know. But this is using pipelining on computer. And basically the way I recorded this is that I take an SBT project, turn on pipelining, and then do clean, compile like 8 times. And then I take the average. So with Chess, it's this open source web server for chess. Basically, the story was that I got a 25% reduction here in the time that it takes, but an equivalent increase in the memory usage because of the increased parallel compilation. So more things in parallel means more memory. But it was, a significant reduction in the time used. So this is something to think about. I think Lichess have restructured their build since I recorded this because they now report a 10% reduction in speed. But I think overall they did a big restructuring of their build, so it might be faster than when I did this, for example. Yeah, and here are some other projects that I did. So we had Pecco, Akka HTTP, CATS, Scala Dex, the .e compiler, which is Scala 3 compiler. And the best that I found was Scala Dex, which I showed earlier. And we had like a 30% reduction in a real project. So that's quite a good speed up. Yeah, and then the outlining that I showed as well. I did this on the Scala 3 compiler and had those 3 worker threads to speed it up. And yeah, I got, you know, a 1/3 reduction here. So that was quite a good return. So finally I could, yeah, I think I have enough time to just do a little demo of the speed up. So I have a small project here and I have these 4 modules. I have util, core, cleaning and app. And this is what I showed. This is what I showed here. So let's just do this again. So, yeah, I'm gonna clean everything. And let me show the build. So currently, yeah, I'm using this Scala 3.5.0 RC1 and pipelining is turned off. So if I need to do this several times to make sure the JVM warms up. I should turn off the profiling. But you see, like I'm running this about 5 times and it's still taking about 5 seconds to build. So this seems, okay, 4 seconds. That's about the fastest that would go without the pipelining. So if I said, so now I've turned pipelining to true and I reloaded. So it was 5 to 4 seconds to compile before, and now it's 2 seconds. So it's definitely a decent improvement. So try it out, please. Yeah, so 2 seconds, 5 to 2 seconds. So that's a big 50%, 30% speed up. So yeah, that's everything. So thank you for listening. No. And no questions.
No? まだ、ちょっと待ってくださいね。発表ありがとうございました。発表ありがとうございました。それでは質疑応答に移りたいと思います。質問がある方、挙手をお願いします。
Hi, can you change like the issue with macros? Can you change it to automatically detect macros and then just wait for the full compilation instead of failing?
Right. So the question is, can we detect the macros automatically? Yeah, so SBT does actually already automatically detect the macros, but it's not great because the upstream dependencies of the macros might also be pipelined, and SBT can't really detect that. So then you have like some pipeline project that goes into the macro project. The macro project is compiled fully without pipelining, but the upstream project is pipelined. So then there's no class files going into it. And that's where you get that it's like a transitive problem. And I don't know how solvable that is.
Okay, thanks.
ありがとうございます。他に質疑応答ある方いらっしゃいますでしょうか。挙手お願いします。
Hi, a question. You show some performance on some libraries like Pecco, Akka, and I was curious why Pecco, for example, there was so few improvement. Do you know? Have you looked into that?
I don't remember. This was over a year ago that I did this.
Okay, sorry, thank you.
ありがとうございます。他に質問ある方いらっしゃいますでしょうか。どうぞ。後ろの。
ありがとうございます。美しいそのパイプラインの流れだったと思うんですけれども、何かその参考にした言語とかプロジェクトっていうのはあったりするんでしょうか。またそれともなんか試行錯誤の結果、こうなったっていう感じなんでしょうか。
Do you mean specifically these projects up here are trial and error or something else?
と言いますか、なんかそのスカラのその3.5のパイプラインのこの流れがっていうことですね。が、まあなんか他の言語とかのインスピレーションを受けてるかみたいな。それです。
So you mean the diagram?
いえいえ。
I don't know. Thank you for enjoying my diagrams. I draw them all myself. I don't know. It's just Google Docs. Yeah. I hope that answered the question. So this work was already done by I think by Morgan Stanley in the Scala 213 compiler. So I was mainly porting this to Scala 3.
なるほど、わかりました。ありがとうございます。
Sorry.
ありがとうございます。もう少し時間がありますが、何か質問ある方いらっしゃいますでしょうか。では、まず前の方にお願いします。
リモートキャッシュが途中まで対応できてなくて、後から対応したという話だったと思うのですが、それは何が難しかったのでしょうか。
Thank you for the question. So I didn't implement this feature in SBT, but I did implement the Scala 3 compiler interoperation with SBT. One of the challenges was we have this requirement to support older versions of SBT before 1.4 and after. And one thing was we had to basically create another bridging abstraction so that we could support both one and the other. But that wasn't so complicated.
ありがとうございます。
ありがとうございます。あと一つぐらいですかね。何か質問ある方いらっしゃいますでしょうか。そしたらお願いします。
途中、マクロがサポートされてないというか、コンパイルエラーになるといった話 があると思うんですけれども、後のバージョンでそれに対する対応などの予定はありますか？
So, actually, this is a fundamental problem that's running to run a macro. We need the class files from the macro code, and that would require running to the end of the compilation to get these class files. And so it doesn't make sense unless we redesign how macros work to not use class files. So potentially we could redesign macros so that they interpret tasty, but this is a very difficult problem and probably won't happen. So I recommend instead to try as much as possible to use inline methods and not macros. Because inline only needs tasty.
はい、大丈夫ですかね。はい。では、そろそろ時間が来ましたので、こちらのセッションはこれで終わりたいと思います。改めて、ジェイミーさん、ありがとうございました。